Let's try to keep ourselves out of some more trouble spots. Let's suppose you have this integral. People who really practice their algebra a lot might notice, hey, there's an x in every term here. I can factor that out. So we might say, can I pull the x all the way out and write x times 5 to 7, integral 5 to 7, x cubed minus x to the 1 plus 19 dx. Does that work? Well, remember, this is a definite integral. Its answer should be a number. So a definite integral, answer is a number. Not involving x. This is a definite integral. Its answer is a number. But then we have x times that, so overall, this is a formula involving x. It's not just a single number. So these two things cannot possibly be the same. You can't factor a variable that's the variable of integration out in front of an integral. What if we don't try to pull it all the way out? What if we just pull it out to here, x cubed minus x plus 19? It turns out this is true. You can factor that expression inside the integral, but it's not helpful. Integrating this would be just a simple polynomial integration, right? Power rule on this, power rule on that, power rule on that. But this with a product of two functions, each of which involves x, we would need something like a product rule for integrals. And there is something like a product rule for integrals, but it's a Calc 2 thing, and it's called integration by parts. So to this we'll say true but not helpful. You have to wait until Calc 2 to do the integral of a product of two functions. Okay, so we can't save ourselves any time there. Let's do this two ways, both without factoring. One way would be to say, there's two ways we can go about this. We could say the integral of a sum, that's the integral of sum or difference, is the sum of the integrals. So we could say this is equal to the integral 5 to 7 x to the 4th dx minus the integral 5 to 7 x squared dx plus the integral 5 to 7 19x dx. And then take the antiderivative of each of those. We could say this is 1/5 x to the 5th from 5 to 7 minus 1/3 x to the 3rd from 5 to 7 plus 19 1 times 1/2 x squared from 5 to 7, which is true. But there's a more streamlined way. We can say, let's take the antiderivative of each term as it is and just do the 5 to 7 all at the same time. So we could say this is 1/5 x to the 5th minus 1/3 x to the 3rd plus 19 times 1/2 x squared from 5 to 7, which is also true. Which of these seems better? Well, some people like this one, but the reason I like this one is I could type this all in as big F of x, and then in Desmos, I could say big F of 7 minus big F of 5, and I'm done. There's no point taking time to plug in, for problems like this, there's no point taking the time to plug in the 7 and the 5 by hand and dealing with fractions and stuff. I would just tell Desmos, here's my antiderivative function that I got by hand, and then please evaluate it at 7, evaluate it at 5, take the difference, and we're done. The extra nice thing about this is then you can graph that big F function, that's your antiderivative, and you can mentally check or even ask to see f prime that you get the original integrand. So we'll say also should graph big F of x if you tell Desmos that's big F of x. You could do that separately for each one, but that's going to be a lot of pain. You'd have like 3 Desmos windows open or something. So you can graph big F of x to check it. There are a lot of times in applications where we want to see the antiderivative function. And this isn't an application, but in real applications, we might want to see the real cumulative change so far function. And so you want to do that all as one piece. And then we can also do f prime of x and check that it's equal to f of x by overlapping. I mean, click the f prime on and off and see that it overlaps big F.